Hello. Today I'm going to be talking about rule-based expert systems. These are what spring to many people's minds when you talk about artificial intelligence, and indeed they are a fairly easy topic to understand. An expert system is a program designed to take facts and answers to questions supplied by the user and draw some useful conclusion based on them. It might be used, for instance, to diagnose some medical problem. Does the patient have an unusually high temperature? What's the concentration of such and such a chemical in the bloodstream? That sort of thing. Or it could offer financial advice based on a user's financial position and needs. Or perhaps decide whether an applicant should be granted or refused a mortgage. Essentially any situation where a human expert is required to offer advice or a decision can be encapsulated in the form of an expert system. Generally, we talk about rule-based systems to describe expert systems that consist of a discrete set of rules. I've shown a couple of examples here. Such systems contrast with connectionist nets, in which expertise is spread out more amorphously over a network of nodes and connections. Looking at those rules, it should be fairly easy to work out what they're for, particularly since each one comes with a brief explanation. The expert system in question is for identifying animals from observations made by the user. Occasionally it will ask a question to prompt for more information, and in the end it will say the animal is a whatever. Rule 315 puts the question up on the screen. Does the animal have fur or hair? If so, then it must be a mammal, and the system stores that information in a variable called mammal, set to true or false. It's worth noting that this question is only asked if Rule 315 is called. It might be possible to identify the animal without knowing whether it has fur or hair, in which case why ask the question? A well-constructed expert system should ask questions intelligently, and only the minimum number it needs to ask in order to be sure of its conclusion. Rule 422 takes two pieces of information, whether the animal is a mammal and whether it can fly, and draws a conclusion based on them. Those pieces of information don't have to come from questions put to the user, of course. They can be worked out from other pieces of information earlier on. Take whether the animal is a mammal or not. We've already seen that having either hair or fur makes you a mammal. Another characteristic is that they give birth to live young, rather than laying eggs. They suckle their young and are warm-blooded. These characteristics can be used in the negative. If the user observes that the animal in question lays eggs, or has scales, then that's a sign that the creature isn't a mammal. So if the expert system learns somehow that the animal lays eggs, it can set the variable mammal to false, and it doesn't need to ask about hair or fur or breastfeeding babies. Of course, there are exceptions that throw grit in the gearbox. Birds, which aren't mammals, are also warm-blooded. Great white sharks also give birth to live young, in spite of the fact that they're fish, and that's without mentioning the group of egg-laying mammals that are the monotremes. If you choose to include these animals in your expert system, and it might be easier simply to forget about them, then they will make the rules more complicated, although they are part of life's rich tapestry. Just about every lecture I've attended on the basics of expert systems has started with the advantages of expert systems over a human expert, and who am I to differ? Having said that, there's nothing on this list that applies specifically to expert systems. The advantages that I'm going to list apply to just about any computer program that's set to replace a human worker. We've already seen the fact that expert systems can be written with an explain facility, allowing the user to get some sort of grasp on how it makes its decisions. Such a feature might also be used in human tuition, like a teacher explaining some point to a student. Expert systems are reasonably cheap to produce, as the only appreciable cost comes from actually extracting the knowledge from the expert. Once that has been turned into a series of rules, the work is essentially done, with the possible exception of testing and field trials. If the knowledge already exists in the form of, say, a semantic net, then there are automatic techniques for turning that into a rule-based system, just as there are techniques for extracting rules automatically from very large sets of data, although they're quite primitive at the moment. That's called data mining, and I'll be talking about that in a future video. Once the expert system has been created, then the only real cost lies in keeping it up to date. The program itself can be made widely available over the internet, or sent in all directions around the country on digital media like data sticks. Human workers are fallible and can easily make mistakes when working long hours or under pressure. If programmed correctly, an expert system will continue to give the right decision indefinitely and never loses focus. You might object to the idea of putting your life in the hands of a computer program, but it happens on a regular basis, such as in the automatic flight controller on a commercial aircraft. The human pilot enters a specific course that the plane should follow, and then leaves the autopilot to it. In this case, the expert system continually reads its information not from a human being, but by testing the conditions of various sensors on the aeroplane, such as the airspeed, height, orientation of the plane, that sort of thing, and gives its output not in the form of human-readable text, but by altering the positions of the controls, such as the wing flaps. If the expert system makes any mistakes, the plane drops from the sky. A similar critical situation, where the expert system cannot afford to make mistakes, is in controlling a nuclear power plant. Again, the input comes in the form of various physical observations, such as temperature or radioactivity levels, and the outputs in the form of setting various controls to ensure the system is safe and that power continues to be generated. In this case, the expert system is also supposed to show the state of the power station at any moment on a large display board, so that the human beings can intervene if they deem it necessary. Another advantage of expert systems is their permanence. Once the expertise has been captured, it is in a form that is potentially immortal, as it can be copied as many times as you like without any degeneration of the signal. If copies of the expert have been distributed far and wide, then even if the original computer on which it was stored is shut down, the program will continue to run elsewhere. While file formats and programming languages become obsolete or fall out of favour, the data itself can be translated into new formats to use in whatever the replacement is. Of course, that might prove a problem if an error or omission is found in the expert system and a new version has to be released. If there are many copies in use all over the globe, then it's the devil's own job trying to get them all updated. Often, more than one human expert will be called in to investigate tricky cases, and this can lead to the too many cooks problem. If Dr. A says the disease is one thing, and the equally prestigious Dr. B says it's something else, whom do you believe? In expert systems, the expertise from more than one expert can be captured and blended. Various automatic techniques, such as mixture of experts, can be used to decide which parts of the system take precedence if there is any disagreement. Alternatively, each human expert can be used to construct just the module of the program for which he is best suited, and allow the other modules to be based on the experience of others. This produces something which should contain the strengths of all the experts and is the best of all worlds. Of course, it does assume that all experts can, if not agree on every situation, then at least come to some sort of compromise solution. That does assume that the expert system is indeed created out of modules with a defined interface between them. If that is the case, then changing an expert becomes as easy as removing a particular module and replacing it with an updated one, while ensuring that it communicates correctly with the other modules in the system. Finally, unlike many human experts, machines are never emotional and will always give you a coldly logical decision every time. There's no need to say, "Give it to me straight, Doc," to an electronic doctor, as you can be sure that it will, however devastating the news is. In a highly pressurized situation, such as whether to launch the nuclear missiles or not, you would not be waiting for the commander to stop dithering and come up with a decision. It would give you the best decision that it could the moment it had all the facts available. Bearing that in mind, perhaps machines aren't best suited for the job of command, as a bit of humanity might be needed. In beating the drum for expert systems, one thing AI lecturers tend not to concentrate on is the list of disadvantages to replacing a human expert with a machine. You've already touched on one or two of them, namely the fact that it is difficult to update an expert system if it is already in widespread use, simply because of the countless copies orbiting out there. Of course, if everyone using the expert system logs onto the one and only copy of it on some web server at the other end of the internet, then that ceases to be a problem. One problem with expert systems is the work required in extracting the knowledge from the human experts in the first place. A consultant or professor with many years' experience in his field is so familiar with his field of study that he's at the point where he can work by instinct. So if you go to him and ask him to categorize and codify his reasoning into solid rules, he might well find it an impossible task. Even if he can come up with a set of rules, they might well be hedged with lots of ifs, buts and exceptions. This is, incidentally, the flip side of one of the advantages of expert systems, which make their knowledge explicit. And what happens if that expert system makes a mistake at some point in the future? Perhaps a catastrophic one. With expert systems flying our planes, tuning our car engines continually as we drive, and controlling our power stations, any mistake they might make could well result in the deaths of several or many people. Who is to blame in that case? The human programmer? The computer? The operator at the time, such as the driver or pilot? Or perhaps nobody? There have been a few fatalities, caused by artificially intelligent devices, but the issue of legal responsibility in AI is still wide open. Rule-based expert systems have the following general structure. Those horizontal lines indicate individual rules, which, as you've seen, generally consist of an if part, a conditional part, and a then part, a conclusion. Each rule can be assigned a priority number to indicate how important it is, so that the more important rules take precedence over less important ones. Similarly, rules can be grouped into sections, if the problem under consideration allows it, with each section given a priority number. The program probably starts by asking the user to provide some basic information to give it something to work with. Then the inference engine, which is the meat and potatoes of the expert system, takes a set of rules and compares each of them to the facts as they are currently known. Some of the rules are triggered, i.e. activated. This could be either because they are simple questions, like that rule that you saw that asks whether the animal has hair or fur, or because every part of their if sections has been satisfied. Take that other rule that let you identify whether the animal was a bat or not. The if part consists of two parts. Was the animal a mammal, and could it fly? If the known facts are yes for both of those, then the rule is triggered. If either one of those is don't know, then the rule is not triggered, but it is still available for later use. If either one of those is no, then the rule can't be triggered at all, even if the other one is yes. It's dead for the remainder of this session. Several rules might be triggered, but at each stage only one can fire. Many are called, only one is chosen. This is where the priorities come in. If the rules have priorities or they're in groups which might have priorities, then some algorithm is used to decide which one of those triggered rules fire. This then changes the known facts available to all the other rules before dying. The rule has shot its bolt and is of no further use for this session. This procedure repeats with different rules being triggered and firing until some terminating condition is met. This might be to report success of some sort and present the conclusion, or to admit defeat if the data available wasn't enough to draw any conclusions. The expert system might be able to report partial success, e.g. it might have concluded that the animal is a centipede of some sort without being able to pinpoint a species, or that the blood disease is caused by an enzyme deficiency of some sort, but not exactly which one. Of course, if the expert system is being used to control a nuclear power station or the autopilot for an aircraft, failure is not an option. You'll probably remember the concepts of forward and backward chaining from the lecture on knowledge representation. The sort of reason that we have seen up to now is forward chaining, with observations leading to conclusions. There is a form of backward chaining which is actually pretty similar, except that we look at the rules slightly differently. An early expert system called Mycin, which diagnosed blood diseases, used backward chaining to reason. Different blood diseases lead to different symptoms, and yet the patient presents with the symptoms, and the system has to work backward to identify the disease. Given the list of symptoms, what classes of disease might cause them? What specific disease out of that class of disease are we dealing with here? Mycin could suggest other tests that should be carried out, and, having identified the disease, it could prescribe the correct treatment. I had wanted at this point to talk about a few famous expert systems, such as Mycin and Prospector. However, I think I've talked for long enough, and I don't think I could really do them justice without this video being well over 20 minutes in length. As such, I'll leave it until next week before waxing lyrical about the successes that expert systems have had in the past. It gives you something to look forward to. So, if you're not too disappointed about not getting the full picture on expert systems, you might like to signal it by clicking the like button below. And if you are rather disappointed about my failure to deliver, you could always vent your spleen in the comments section. Either way, please also take the time to click on the subscribe button and click the bell icon in order to receive news about my weekly videos. There's much more to come. Thank you.